On level ground, an early gasoline automobile could appear surprisingly capable. The engine settled into a steady rhythm, the driver found a comfortable gear, and the machine moved forward with enough confidence to suggest that the difficult part of inventing the motor car had already been solved. Then the road began to rise. Speed fell first. The driver opened the throttle farther, asking the engine for more power, but instead of responding cleanly, the motor might hesitate, lose its rhythm, or begin firing unevenly. A lower gear could help. Ignition timing might be adjusted. Momentum became precious. Yet the steeper the gradient grew, the more clearly the car revealed weaknesses that level travel had concealed. The fuel tank was not empty. The cylinders had not suddenly failed. Nothing necessarily had broken. The engine simply found itself operating under conditions far more demanding than those of steady travel on a flat road. Poor hill climbing could have several causes. An engine might lack sufficient power. The available gear ratios might be poorly suited to the gradient, forcing the motor outside its useful speed range. Ignition could be weak or incorrectly timed. Cooling limitations became more serious under sustained load. Fuel might fail to reach the carburetor reliably, and even when gasoline arrived. The device responsible for mixing it with air might produce a mixture that worked under one condition and poorly under another. The carburetor, therefore, was not the single explanation for every early car that struggled uphill. The deeper problem was that a road engine had to keep working while load. Speed, airflow, temperature, and fuel demand changed continuously. It did not merely need gasoline. It needed gasoline in a usable form and in a proportion the engine could burn effectively at that particular moment. Liquid fuel cannot simply be poured into a cylinder and expected to produce efficient combustion. Gasoline has to mix with incoming air so that enough of it is vaporized or divided into fine droplets before ignition. Too little fuel can produce weak or irregular combustion and a loss of power. Too much may cause poor running, hesitation, fouled spark plugs, or wasted fuel. The useful mixture range is broad enough for an engine to operate under many conditions, but it is not so forgiving that early designers could ignore the relationship. More difficult still, the mixture behavior that works at steady road speed may not be ideal at idle during acceleration, or when the throttle is wide open and the engine is pulling hard. The earliest carburetors appeared at a time when merely creating a combustible charge was an achievement. Surface carburetors allowed incoming air to pass over gasoline and pick up vapor before entering the engine. Some used absorbent material soaked in fuel, others exposed a larger liquid surface to the airflow. These arrangements could make an engine run, which was the immediate requirement, but road vehicles quickly demanded more. Fuel volatility changed with temperature, contamination could affect passages, and mixture formation was not always consistent as airflow varied. A stationary engine operating near one speed could tolerate such limitations more easily. An automobile could not. The engine might idle at a roadside stop, accelerate away, cruise for a few minutes, then face a steep grade that forced the driver to open the throttle while road speed fell. The fuel system had to respond without knowing anything about the road itself. Wilhelm Maybach became one of the important figures in improving this process. Working with Gottlieb Daimler, he developed a spray nozzle carburetor during the 1890s. Instead of depending mainly on air collecting vapor from a broad gasoline surface, fuel could be drawn through a nozzle into a moving stream of air. The airflow helped break the gasoline into smaller droplets and carried it toward the cylinders. The device was more compact and better suited to the increasingly fast-running gasoline engine. It also helped establish the basic arrangement that would dominate carburetor development for decades: a controlled fuel supply, a metering jet, an air passage, and a region where airflow created the pressure difference needed to draw gasoline into that stream. For the system to behave consistently, the fuel at the jet had to remain near a predictable level. The float chamber addressed that need. Gasoline entering the chamber raised a float, and as the fuel approached the desired height, a needle valve reduced the incoming flow. When the engine consumed fuel and the level dropped, more gasoline entered. This did not regulate the entire air-fuel mixture by itself, but it provided a stable reservoir from which the jet could operate. On a moving automobile, however, fuel first had to reach that chamber. Many early cars relied on gravity feed. The logic was attractive. Mount the tank above the carburetor and allow gasoline to flow downhill through a pipe. No pump was required. There were no additional moving parts to wear or consume power. Under ordinary conditions, the arrangement could be simple and dependable. A steep ascent changed the geometry. Contemporary engineering texts warn that if the vehicle tilted enough, the carburetor could effectively rise above the level of the gasoline remaining in the tank. At that point, gravity no longer favored flow toward the engine. The car might still carry fuel, yet behave as though the tank were empty because the gradient had placed the fuel at the wrong level relative to the carburetor. This was not a mixture calibration problem. It was a delivery problem. The distinction matters. A poor carburetor can meter gasoline badly even with a completely full float chamber. An excellent carburetor cannot help if no gasoline reaches it. Pressure feed systems offered one answer by applying modest pressure above the fuel in the tank. Vacuum arrangements later used engine suction and an intermediate reservoir to lift gasoline from a lower main tank before allowing it to flow toward the carburetor. Mechanical pumps eventually made tank location far less dependent on gravity. These systems reduced one of the road angle problems, but once fuel delivery became more dependable, another weakness became harder to ignore. The simple jet did not meter perfectly across the engine's entire operating range. In a basic spray carburetor, stronger airflow and suction at the jet do not necessarily increase fuel and air in exactly matching proportions. As engine speed and airflow rise, a simple main jet can tend to enrich the mixture progressively. That behavior may be acceptable within a narrow range, but an automobile engine cannot remain at one operating point. At idle, the throttle is almost closed and airflow through the main passage is weak. During cruising, the engine settles into a more stable condition. Acceleration changes the pressure relationships rapidly. On a difficult gradient, road speed can fall while the driver opens the throttle farther, and a downshift may suddenly increase engine speed. One fixed jet must somehow behave acceptably across all of these changes. Early motorists could compensate to a degree with manual mixture controls. A skilled driver listened to the engine and learned when an adjustment helped. Such skill could make a primitive fuel system appear far more capable than it was in inexperienced hands. Yet automobile manufacturers were trying to move in the opposite direction. They wanted fewer procedures, less specialized knowledge, and engines that responded consistently without requiring the person behind the wheel to diagnose mixture strength while climbing a hill. Francois Baverey became central to one of the most influential attempts to make carburation more self-correcting. Born near Lyon in 1873, Baverey came from an industrial background rather than the established automotive companies that had dominated early engine design. In 1903, he acquired a Lorraine Dietrich and became dissatisfied with its engine behavior. Historical accounts associated with the later Zenith company describe poor running and irregular fuel delivery among the problems that drew his attention. Baverey concluded that a conventional single-jet carburetor did not maintain a satisfactory mixture as engine speed changed. Beginning around 1905, he worked on a system that could compensate automatically for that tendency. His French patent followed in June 1906. The principle he developed was elegant because it did not simply increase fuel flow. It added another fuel path whose behavior differed from that of the main jet. In a simple carburetor, the main circuit tends naturally to make the mixture richer as suction grows. Baverey's compensating arrangement supplied fuel in a way that countered that tendency. The contribution from the compensating circuit changed differently as airflow increased, so the combined delivery of the two could remain within a more useful range. The carburetor was therefore beginning to correct one of its own predictable errors through fluid behavior alone. There were no sensors, no electronics, and no feedback computer examining the exhaust. Jets, fuel levels, calibrated passages, and pressure differences performed the correction. That was the main engineering reversal. The carburetor was no longer simply admitting gasoline whenever airflow created suction. Its internal arrangement could shape how fuel delivery changed as the operating condition changed. The value becomes clearer when the engine encounters a hill. At the bottom of the grade, road speed may be relatively high and the throttle only partly open. As the slope steepens, the driver asks for more torque and opens the throttle farther. If speed continues falling, a lower gear may be selected, increasing engine revolutions, even though the car itself is moving more slowly. Through that sequence, airflow, manifold depression, throttle position, and rotational speed all shift. The carburetor must continue providing a charge the engine can use, while those variables move in different directions. Better compensation widened the range over which useful mixture could be maintained. It did not turn the Zenith carburetor into a magical hill-climbing device. Gearing still mattered enormously. An engine unable to produce sufficient torque could not be rescued by perfect mixture alone. Ignition timing, compression, cooling, vehicle weight, tire grip, and gradient remained important. Altitude introduced another complication because air density decreases with elevation. A carburetor calibrated near sea level may deliver a relatively richer mixture at high altitude because the same volume of air contains less oxygen. Drivers crossing mountainous regions could therefore experience power loss even when the fuel system itself was functioning exactly as designed. Baverey's achievement was valuable because it improved one variable engineers could control rather than pretending the others did not exist. His work developed into the Zenith carburetor. Rocher Schneider in Lyon provided manufacturing support, and by the late 1900s, Zenith systems were moving into broader automobile use. Their success reflected how rapidly carburation had become a specialized field. Only a short time earlier, engineers had been satisfied to produce a mixture capable of keeping an engine running. Now they were concerned with how that mixture behaved through an entire range of speed and load. The main circuit, however, was only one part of the developing problem. At idle, the throttle plate is nearly closed and airflow through the principal venturi may be too weak to draw fuel effectively from the normal main jet. Engineers, therefore, added separate idle or slow-running passages positioned where pressure conditions remained useful when the throttle was nearly shut. As the throttle opened, another difficulty appeared. The engine had to move smoothly from the idle circuit into normal main system operation. If fuel flow did not increase quickly enough, the mixture could become temporarily too lean, and the engine would hesitate just as the driver asked it to accelerate. Progression passages and later accelerator pumps helped bridge this transition. An accelerator pump could deliver a brief additional quantity of gasoline when the throttle moved rapidly, covering the period before ordinary airflow through the main system established the new fuel rate. Heavy load operation required still another compromise. A carburetor calibrated only for maximum power could waste fuel during long periods of light cruising. Yet an engine operating near full load might need mixture behavior different from economical steady running. Later designs added enrichment mechanisms that responded mechanically to throttle position, manifold pressure, or other conditions. The fuel system had stopped being a single jet performing one universal task. Different circuits now handled specific regions of engine operation, often overlapping, so that transitions occurred smoothly. To the motorist, most of this remained invisible. The throttle control still seemed simple. Inside the carburetor, several passages could be active in different proportions, depending on engine speed, throttle opening, and load. Such complexity was not evidence that carburetors were fundamentally poor devices. It reflected how much was being demanded from the road engine. Unlike a stationary motor that could operate near one governed speed for hours, an automobile engine had to start cold, idle, pull away, cruise economically, accelerate, climb, descend, and repeat the sequence many times during a journey. Ambient temperature affected vaporization. Fuel formulations varied. Wear changed vacuum and compression. A useful carburetor had to tolerate those differences without becoming too fragile or expensive to manufacture. Fuel delivery upstream evolved for the same reason. Gravity feed had served well when tank location and vehicle layout allowed it, but designers increasingly wanted the freedom to place the fuel tank according to balance, body design, safety, and passenger space. Vacuum tanks provided an intermediate solution. Pressure feed systems appeared in other applications. Mechanical pumps eventually became widespread and allowed gasoline to be drawn from tanks, mounted lower and farther from the engine. Once fuel supply became less vulnerable to the angle of the road, the carburetor could concentrate on metering rather than depending on favorable geometry between tank and float chamber. By the 1920s, technical discussion of carburation increasingly revolved around main jets, compensating circuits, slow-running systems, chokes, auxiliary air control, and transition behavior. The standard of success had moved far beyond simply vaporizing gasoline. This also changed the relationship between car and driver. Pioneer motorists often operated mixture controls manually while also managing throttle, ignition timing, and gear selection. A difficult hill became a test of both the automobile and the operator's mechanical understanding. Choosing a lower gear too late could allow the engine to fall below its useful speed. Incorrect ignition timing weakened combustion. Poor mixture adjustment might cause stumbling or excessive richness. Improved carburation reduced some of this burden by making the fuel system respond automatically to conditions that previously demanded attention. Manual chokes and mixture controls survived for decades, so the change was gradual rather than absolute. Still, the direction was unmistakable. More of the work required to maintain useful combustion was being built into the mechanism. This was especially valuable because the mixture itself was invisible. A driver could hear misfiring, feel hesitation, or see smoke, but those symptoms did not uniquely identify the cause. Weak ignition, excessive fuel, inadequate fuel, overheating, or simple lack of engine power could produce overlapping complaints. The more consistently the carburetor behaved, the less often the motorist had to diagnose the problem while moving. Automatic compensation, acceleration enrichment, and better fuel feed allowed the throttle to become a more dependable request for engine output rather than an invitation to adjust several other controls. Carburetors never became perfectly adaptive. Their behavior was determined by physical hardware: jets, springs, passages, floats, diaphragms, air bleeds, and calibrated restrictions. They did not directly measure the oxygen content of the exhaust or calculate corrections thousands of times per minute. Altitude continued to reveal their limitations. Lower air density could upset a calibration chosen for sea level. Cold weather affected both vaporization and starting behavior. Hot conditions created different concerns. Engineers developed increasingly ingenious mechanical solutions, but each correction required another passage: valve, linkage, or calibrated element. The success of carburetor engineering therefore helped establish why greater precision was valuable. Fuel injection pursued the same objective by another method. Instead of relying primarily on venturi suction to draw gasoline from a jet, injection systems could force measured fuel through an injector. Mechanical injection appeared in specialized and high-performance applications before electronic control became widespread. Later, electronic systems added sensors for variables that carburetors could only infer indirectly. airflow or manifold pressure, throttle position, coolant temperature, intake temperature, engine speed, and eventually oxygen content in the exhaust. A control unit could alter fuel delivery continuously as conditions changed. This did not make the carburetor a historical failure. Carburetors successfully powered automobiles for most of the 20th century, from economical family cars to powerful racing engines. Their sophistication eventually became extraordinary. Multi-barrel designs could limit airflow during light driving and open additional capacity when more power was needed. Metering rods changed effective jet area. Vacuum-operated secondaries controlled when extra airflow became available. Accelerator pumps, power valves, air bleeds, emulsion passages, and automatic choke systems provided levels of control the pioneer motorist could hardly have imagined. A carefully tuned carburetor could deliver excellent performance and drivability without electronics. Its limitation was that most of its corrections had to be built into hardware in advance. Electronic injection could adapt more flexibly because sensing and software replaced some of those fixed compromises. The road from the primitive surface carburetor to electronic fuel control was not a sequence of unrelated inventions. Each stage answered the same broad requirement with better tools. Surface systems tried to create enough vapor to sustain combustion. Spray nozzles improved the way liquid fuel entered the air. Float chambers stabilized the level at the jet. Compensating circuits corrected predictable mixture drift. Separate idle and enrichment systems handled operating regions. The main jet could not serve well. Fuel pumps made supply less dependent on the position of the tank. Injection finally allowed fuel quantity to be controlled with much greater independence from the airflow mechanisms that defined the traditional carburetor. A steep climb remained an especially revealing test because it combined several stresses at once. The engine had to produce greater torque, while vehicle speed could be falling. The driver might open the throttle farther and then select a lower gear, abruptly changing engine revolutions. A gravity-fed tank could encounter an unfavorable angle. At altitude, reduced air density complicated mixture behavior further. From the driver's seat, these different failures might all feel like one complaint. The car had no power. To an engineer, they were separate problems that required separate solutions. That distinction is what makes the history more interesting than the simple claim that early carburetors could not climb hills. Maybach's spray nozzle carburetor improved mixture formation. Float control made the fuel source at the jet more stable. Vacuum and pump systems reduced dependence on gravity. Baverey's compensating principle addressed a characteristic weakness of simple jet carburation as airflow changed. Auxiliary circuits later handled idle, transition, acceleration, and heavy load operation with greater finesse. No single improvement transformed the automobile alone. Together, they expanded the range of conditions in which a gasoline engine could operate without demanding constant intervention. The Zenith story represents that transition particularly well. Baverey's important insight was not that engines simply needed more fuel. He recognized that a carburetor could be designed so one part of the system counteracted the natural mixture error of another. The mechanism did not know the car was climbing or accelerating. It responded only to pressure, flow, and fuel level. Yet that response allowed the engine to tolerate a wider range of road conditions with less manual correction. This principle points toward the larger history of engine management. As road demands became more variable, the fuel system had to become less dependent on one fixed setting. By the mature carburetor era, motorists could climb gradients that would have tested pioneer machines without thinking about jet compensation or float height. The driver selected a suitable gear and pressed the accelerator. Behind that simple action, the fuel system maintained its reservoir, metered gasoline through calibrated circuits, added enrichment when required, and delivered a combustible charge to the engine. The hill had not become easier, and gravity had not changed. What changed was the automobile's ability to respond without exposing every weakness directly to its operator. That is the deeper significance of early carburetor development. The breakthrough was never merely supplying more gasoline. Too much fuel could be as harmful to performance as too little. The real advance came from learning to regulate when fuel arrived, how it entered the airflow, and how its quantity changed as the engine moved from one operating condition to another. Maybach helped improve the spray process. Baverey's Zenith system showed how mixture behavior could be compensated mechanically. Later engineers extended those principles until carburetors became remarkably sophisticated devices, and fuel injection eventually pushed control far beyond what fixed jets and passages could achieve. Yet the engineering question had already been exposed by the earliest difficult gradients. A gasoline engine could not become dependable simply by carrying a full tank. The hill did not demand more gasoline alone, it demanded better control of gasoline. And that distinction helped turn the fragile early motor car into an engine that could follow the road wherever it went.